en el Research Center for Astronomy Academy of Athens, Greece. Bueno, creo que ya no los voy a cansar yo, mejor escuchamos a Panos con su plática.
Thank you. I have one. Yeah, thank you. So many thanks for the invitation and the introduction and everything. I'm very glad to be with you. There are always, let's say, contacts, at least in the research level, between Greece and Mexico, and the common point is dynamics. So there are people in Mexico working in dynamics, Barbara, Marco, many people also in the past. So we read each one the paper of the other group, right? At least at this level there is a connection, and I'm glad that now we have some more intense links, also with Ivanio, and now also with Barbara, etc. So I feel among friends, and I'm glad to present one talk that will be, as you will see, the background of what I'm going to say is the dynamics of three-dimensional systems, and the application on that will be on bars. Bars for us are on the sky, bar galaxies, right? It's not bars. So, and I will tell you, I'll try to tell you how one can produce Boxy structures in the bars of the galaxies. So, okay, just to make it, to convince you, this is the stuff that I'm gonna talk about. Here we have a famous object. This is NGC 1300. Some observations we got several years ago now with Preben Grossball at VLT with this instrument here, Hawkeye. This is a near-infrared image of this galaxy, famous one. And here is another image that we see a galaxy edge on. This one has two companions. This is taken in Greece with our 2.3-meter telescope called Aristarchos. You may have heard about Aristarchos of Samos, an ancient Greek astronomer. We give ancient names to whatever we have there in astronomy. And here, as you will see, there is a general consensus now among the dynamicist community that when you see this nice structure, the peanuts, as we say here, this is the bar, or part of the bar, actually, to speak more accurately. So this is the stuff we're going to deal with, and there are two ways to approach the dynamics of such systems. Either you get as many mass particles you can, and you let an n-body simulation run. This is what the majority of the colleagues do in the community. The other way, sounds old-fashioned, is to assume a gravitational field and try to understand the dynamical mechanisms behind the structures that you observe. Okay, there are two approaches. Both of them have advantages and disadvantages. Since I'm going to focus on the dynamical mechanisms, in this talk I'm going to use a very, let's say, analytic and simple way of describing these mechanisms. So, assumptions. The first and main assumption is that over a period of, let's say, several gigayears, few gigayears, if you want to be more conservative, the potentials, the dynamical potentials of these systems do not vary, do not change dramatically. And we have support from theory, from observations, and also from the n-body simulation. So a bars stay with more or less the same potential for several gigayears in many n-body simulations. For the spirals, it is less clear, but in any case, this gives us the right to say, look, we're gonna treat our dynamical systems, the bars, as autonomous Hamiltonian system. That means, as you know, time independent. And since these parts also rotate, the Hamiltonian that you can write down to start your investigation is something like this in most of the cases. So here is the potential, the one that we do plausible assumptions for writing it down, and this term here is just for taking into account Coriolis forces, etc., so that we work in the rotating with the bar frame of reference. this is, some of you that are in the dynamics, you know that this is the standard procedure. So this is nothing special. We call this quantity that I have in the ellipse there the effective potential. So this is where we have to go to write down our equations of motion and try to see if we give to a test particle some initial conditions where will go in this field, which will be its path, its trajectory. Okay, just since several times I get these questions and we write that in the paper, we loosely call this Jacobi integral the energy, which is not exactly the energy, but we're gonna call, when I will be saying the energy during my talk, I will refer to this constant of motion, which is the Jacobi integral. Okay, so far so good. Now, here we have a standard tool for understanding the dynamics in the kind of the systems like the one I have shown you before. This is theory that goes back to the end of the 19th, beginning of the 20th century with Henri Poincaré, who visualized the stability of the trajectories in these Hamiltonian systems, in conservative systems, with this self-section. So what it is simply here depicted is that you have in your system a trajectory. It was, if you have observed, 2 degrees of freedom. So we have 2 positions, 2 generalized angular momenta, 2 velocities if you want. Okay? And then the system is conservative. That means from the conservation of from the integral I have shown you before, this Jacobi integral, we can express one of them as a function of the 3 others. So we reduce the degrees of freedom from 4 to 3. And then, as Poincaré suggested, we consider a surface of section. For instance, if we have x, y, x dot, y dot is expressed as a function of the 3 others. If we consider y equals 0, then we have just 2 free parameters, 2 coordinates that vary, x, x dot, or px as I have it there. And what Poincaré proposed was that just consider this surface of section, this cross section, and register the cut, the intersection of the orbit with this plane in one direction only. And then, like this, if you do that, you get figures like what I have here. And there, immediately, you can separate the order from the chaos just by looking at it. And it's exactly these 2 kinds of behaviors. You see that we have some closed curves around a point. The point is a periodic orbit. So we have our Hamiltonian, we have our equations of motion, we have the system of differential equations, we find periodic solutions, like the one that is in the center of this surface of section, here. If this is surrounded by these closed curves that in the terminology of the dynamical system you will find in textbooks, etc., as invariant curves, then this indicates that this is a stable region, an island of stability, as we say. Practically, what does it mean? If we go in the neighborhood of the periodic orbit, in this case, and we perturb it a little bit, the initial conditions, they will not go everywhere in the allowed phase space, but they will stay close to the periodic orbit. In this case, if you start here, you will close to this, stay in this closed curve. If you go here, then you will stay around here, there, around, etc., etc., until the end of the stability index. So the periodic solutions are not always stable. If it is periodic and you have the exact initial conditions, each time for as long as you integrate, it will go through the same point. It will be always here. The question is what happens in the neighborhood, right? So there can be another case where you have one point. You integrate for infinity if you have we can be that precise, the initial conditions will go through the same point. However, if you go in the neighborhood, then it will scatter around in the phase space. And this is one of these cases. Here I point to a point that if you start in the neighborhood, it will go all where in this area where you see this scattered point. This is an unstable periodic orbit, and this is such a regions sometimes you will find in books as chaotic seas. So we have stability regions and chaotic seas. And this was a big help for dynamicists who would like to use this tool for building structures to enhance density in specific places on a galaxy, because the idea was like this, at least until recently, as I will tell you. You find the periodic solutions in your model. In a galaxy, you will never find the periodic orbit, but you want to know what happens in the neighborhood of this mathematical object, which is the periodic solution. And if you calculate and find out that it is a stable one, then you keep it. And then you can just put initial conditions in the neighborhood, they will stay around there, and they will support a structure. Such a structure can be the bar we discussed today, for instance. And look how such quasi-periodic orbits are called the orbits that are around these invariant curves, how they look like in a configuration space. This is the phase space, right? An intersection, a subset of the space. You can look to an orbit that is here and an orbit that is farther away. So these orbits will gonna look as you see here. So one orbit that is close to the periodic one, which is an ellipse. It's an ellipse along the bar. So you go in its neighborhood, you find things like that. This is a nice orbit. If you have many of them, you can build a bar. If you go farther away, you will find something that it is thicker, but also has an overall elliptical shape. Okay, so this was, and still is, what we believe that it is a standard mechanism of building bars. So the stability was associated with the presence of structures. So there are at least 20 years ago now that we started having also some other ideas about how chaotic orbits can help. In practice, we have seen that in several cases, chaotic orbits could support structures. I remember the first discussion about that was the PhD of a friend of mine from the University of Florida, David Kaufman. He did a kind of PhD very close to what I was also doing, but with a barred galaxy, barred spiral, not just a spiral. And then they found out, he and Kontopoulos, who was also his supervisor, was some twin PhD thesis, that some part of the spirals could be supported by chaotic orbits because they were staying for a long time along in the right places. So the idea has been kept in mind, and several years later, I found some orbits like this. And this time, these orbits were in potential. You remember this phi function? I said we do plausible assumptions. Either you take, for instance, for a spiral, a logarithmic spiral formula that is like a spiral you see in the sky, or in other cases, like in that one, the potential was coming from near-infrared observations. There was an estimation of the potential of a real galaxy. Of course, there the parameters that you do not know is the mass-to-light ratio, is the thickness of the disk, etc. But under this, some plausible assumptions, again, you find the potential. And in this potential, we have seen that close to the end of the bar, we had a lot of stuff like what you see there. And these orbits were, by all means, chaotic. We could see on the surfaces of section that they belong to the chaotic sea. That was the first suggestion to say that a bar can be partly supported also by chaotic orbits. And to see what these orbits can do and what parts of the spirals they can suppose, we run some response models. Response models are either let's say, stellar or gaseous, you take an initial disk without any structure on it, with some velocities that are, let's say, close to circular velocities in the axisymmetric part of the potential, so the background potential. You let the perturbation grow for some time, and then at a certain point you have the potential, and then you let the particles, the stellar or the gaseous, do whatever they want. So here is one of these cases. There are free parameters, of course. In this case, the dispersion of velocities was small. If I remember correctly, initially, if you start with circular motion around the center of the galaxy in the axisymmetric part, you got such a response in this case. This is the galaxy, this is the model. Okay, we are quite satisfied. If we added some more dispersion of velocities, we got things like that. The features in all these response models was the same. So we had a bar elongated the same distance as the bar of the galaxy, and we had a surrounding of the bar, which had a boxy structure, which had the same orbital content that enhanced also the spiral arms that you can see here. So, for instance, in this model, or in the previous one, if we can see, this one, the gray stuff at the end is due to chaotic orbits. But certainly, this part, and it was a big discussion later also for the spirals, was supported by chaotic orbits. So what kind of orbits can be these chaotic orbits that support the structure? Let me give you some examples. Here we are, orbits like that. So the only thing that they need to have is the appropriate energy, the energy that can allow them to travel from the disk area, from the bar area, outside the so-called co-rotation region, and visit the space outside. The point is that chaos has nothing to do with randomness. So there are rules in chaos that the particles obey. At the end of the bar are the so-called Lagrangian points that are coming usually in sets, in most of the cases. Two stable, two unstable. And around, about here, close to the ends of the bars, here's the bar, here's the model, let's stay in the model, here and there are unstable points. Close to them, as we have seen in the Poincaré section, if you go to the neighborhood, then the particles will start traveling all around the available phase space, but not taking any path they want. You can calculate some eigendirections. They have to follow these eigendirections, and these eigendirections bring them along the spirals. You see, here, for instance, or there, they do this arc. Here, close to that, it jumps like that. And doing that, they support the spirals. For the time they stay in the bar regions, they enhance structures that can be boxy, looking like orbits that the dynamicists know that look like 4-to-1 resonance orbits, so boxy orbits. So boxiness is enhanced by this kind of chaotic orbits, the spirals as well. And in some cases, things are even more interesting. I want to give you another example of this kind of situation. This is another potential of a galaxy that has been estimated. This is for 1300 actually, but doesn't play any role. It was a paper about finding the dynamics of the galaxy, but the result I will show you, it's I think more interesting than proposing some parameters that match the specific dynamics of a galaxy. It was very interesting to realize that if we take a potential, complicated one, realistic one, you see that we do not have anymore here well-defined co-rotation region with 4 Lagrangian points. As I told you, we have a number of Lagrangian points in several cases. The interesting thing is that you have your potential, then you have the pattern speed with which it will rotate. And then you just vary this omega pattern. And you register the effective potential isocontours. I admit that until that time, this is from a paper with Kavalapoutharakos now in NASA and my mentor, Preben Grosbol, in 2010, I was thinking that, okay, you change the pattern speed and then you rescale this figure. It was not the case. The morphology of the isocontours change from omega pattern to omega pattern. And for a certain value, very close to a good one for the bar, the isocontours had this shape. You may have heard about ANSE type bars, right? So here you have an ANSE type effective potential. What would be the result of that, having such a potential, is that here you have a response model. This is a response model. Here you have an ANSE type bar. You see these contours. Okay, forget about the spirals, which have their own interest. The point is that this white, red, yellow, whatever stuff is made mainly by chaotic orbits. The ellipses that supported the spiral I have shown you before could be found just somewhere here in the center. And all the other stuff you see is just chaotic orbits.
Do you know what is the fraction of the chaotic orbits that are supporting this structure?
This is a response model, okay? So, but these orbits that I have overplotted there are 80%, 90%. It's almost a chaotic bar. But look, here, yes, because it is, one has to accept it, to expect it, because if you go there, you have this isocontour. So if you start any initial condition in here, it will not exceed this initial contour. Here are the Lagrangian points. They do not have the energy to escape. It will stay there. It is like having a well-defined ANSE type and you let a fly in there. It will go all the time and you register its position. At the end it will fill the box. The box has already its own shape. Here is the box, the white stuff. And here, okay, we are trying to match the galaxy. Forget about that. But the point is, I think here is the interesting stuff. I thought that I had some orbits, but are like the ones I have shown you previously. Orbits like that one, they stay there, they do all whatever you can imagine. They even enhance a bulge in here because they stay here, and then as they start going out, they do some excursions, and then they go out. I have the orbits later for anyone who is interested to show you how exactly they are. Okay. Okay, but before closing with two-dimensional systems, I go to this more recent paper with my student, Liana Tsigaridi. It's again two-dimensional. We have taken one of these potentials that we had from galaxies, estimations, etc., and we have treated it as a general potential. So we allowed ourselves to vary far away from the desired value of the pattern speed. So we ran also some very slow models. This was for a Barth spiral system, and here is one of the orbital calculations we did. So mainly, maybe this has nothing to do with a specific galaxy, but it was very interesting to see that in some cases, the bar, which in that case was in here, stopped away from corrotation because we had varied, as I told you, the pattern speed a lot. And the lower the pattern speed of the system, the far away are the Lagrangian points. So in this case, the Lagrangian points are not even are somewhere there, over there, above, close to 10 or something like that. So maybe it's a good place to put for a spiral the Lagrangian points, but not the bar. The bar wasn't the potential. Okay, in this case, we got such a thing, and then we found that it could also, the two-dimensional case, support some Boxy structure with an X embedded in it. You will hear more of that later because I will show you what we did with the three-dimensional models. And again there, it was realized that most of the spirals that were, the orbits that were supporting the bar were from chaotic regions. So we got Poincaré sections in the energies. We did the statistics. We could put at any attribute to any test particle its energy, Jacobi constant. Okay, and then we went on the surface of section and we looked where are these initial conditions that support this Boxy bar. they were around the island of stability. They were all around here. You see all this white stuff around here was giving us orbits to build this boxy bar with the X. And finally, we have seen that this was giving this kind of structures that more recently, we investigated in further detail. At the end of the talk, you will see it's part of the thesis of Leo Chavez Velasquez, which is here in the audience. But just look what we have there. We have orbits like the blue one that supports what we see in the response model, and usually after that we have a ring around that. We're going to explain close to the end of the talk. So what we learned out of all of what I said until now, we do not throw away chaotic orbits. Chaotic orbits can play a substantial role in building structures. Okay? So let's go to three-dynamical system, which will be the main part of this talk. So the formalism is the same. We go to Hamiltonian systems. Now we are in 3 dimensions, however. We have 6 coordinates initially, 3 positions, 3 velocities. Then we follow the same procedure. One of the 6 is expressed as a function of the others, and then we select also a cross-section. Then we have 4, and then it's a problem even for visualizing this as a surface of section. Okay, but this is exactly again what we consider. Again, y = 0 is our cross-section, and here we choose a direction to register the cuts, the orbit as it crosses the plane. Okay. For bars, very, let's say, popular potential from 30, 40 years now until today is the Ferrer's bar. Okay? And this is exactly how the density of the Ferrer's bars here described as a Ferrer's ellipsoid. And for axisymmetric background, where will be the bar located, these are also 2 other popular choices, a Miyamoto-Nagai disk expressed by this function, and the Plummer sphere for having something for a classical bulge in the center. In some cases, you can use also a similar function to have also a halo surrounding the whole potential. In the central parts, dark matter is supposed to be not that important, so for a first approximation, you can forget about that. And let's see how they look like a little bit. So here is how are the isodensity contours of a Miyamoto disk look like, things like that. So like a flying saucer, let's say. Something like, we look now edge on, okay? We have the disk and we look from the side, edge on. And the Ferrer bar gives you also something that reminds a bar, something like what you see down there, okay? This is the environment in which we're gonna work. However, now things start being more interesting from the theoretical point of view. It was this kind of studies were very popular even in the astronomical dynamicist community, because it's a more broad community, this of the people who work in nonlinear dynamics, conservative and non-conservative systems with dissipation, etc. But also in astronomy in the 80s, this was the modern stuff. So how to deal with 3-dimensional dynamical system, Hamiltonian system, what are the implications for orbits like the bars? The point is that we follow the same now procedure as I told you before. We try to characterize first the periodic orbits, these orbits that are mathematical objects. And we don't have, as I said before, and I repeat now, periodic orbits, neither in 2 nor in 3-dimensional galaxies. Actually, we have only 3-dimensional galaxies. But we are interested in their neighborhood, what a particle would do if you go to the neighborhood. And now actually what you do is that you start with one point on the surface of section, and then you want to know where the next intersection will be. If it will stay close to the initial point, like in the 2 dimensions, or if it will fly away. And then for doing that, you have a kind of mapping, and you have a transformation. If you have a transformation, you have a monodromy matrix. And then you are interested about having the characteristic equation, finding the eigenvalues, and expressing with mathematics, let's say, exactly what I say by words, if it will stay close or if it will fly away. And here are two indices that describe, together with this quantity here, exactly describe that. Just for the needs of the talk now, I can tell you, so intuitively you can imagine that if you have, I can show you, I have some figures in the talk. So here are the eigenvalues. So if they stay on the unit circle, then you multiply something by 1. It can not go away. However, you have 4 of them, and then they have also other kind of arrangements. There can be 2 of them on the circle, and then the others on the real axis. Then you have a real number. You multiply, you go away. You can have both of, all 4 of them away, and there is one case where they are all of them in pairs of the axis, like what you see here, pairs, the eigenvalue and the reciprocal one. And this was exactly a main thing to understand, because these two, they had their counterpart to the 2 dynamical systems. You could understand, and they followed the rules for finding new families of periodic orbits that are coming in the system and all that stuff. But here, you didn't know what to do with that. The rules were not anymore respected. This is the kind of instability called complex instability, and we're going to see what are the implications in real systems. Okay, so I will go through the next transparency a little bit fast. The only thing I can tell you is that you know about resonances in galaxies. If you have a rotating body, you can, on the disk of the galaxies, define the resonances. We already spoke about the Lagrangian points and the corotation and all that stuff. In the same sense that we define the resonances with the, in the radial sense, if you are on the plane, then a resonance, for instance, 2 to 1 means that it, by completing a star, a particle, 1 revolution around the center of the system, it will have performed 2 radial oscillations, the so-called epicyclic frequency. You can exactly define the same way with the vertical oscillations. Now, if we say vertical 2 to 1 resonance, it means that by completing 1 revolution around the center of the galaxy, then it will have done quite twice up and down. So it is the same kind of definitions, and we were trying to find what is the correspondence between what we have seen in the second transparency of the talk with this invariant curve surrounding the periodic orbit, what is the corresponding in the 4-dimensional surface of section in the 3-dimensional Hamiltonian systems. And then we had a big problem, of course, how to depict a 4-dimensional object. The solution that we have found, we usually publish now in non-astronomical journals, like in International Journal of Bifurcation and Chaos, that most of this work has been published. There was an initial paper back to '94, and then more recently a PhD thesis did a much more deep study in visualizing these things and of these objects, these structures in the 4D space. And the idea we had was the following. This is what is the best we could think of. We take 3 of the 4 coordinates, and now with the software we have, we can rotate the object and then look how it looks like, so that we understand the 3-dimensional projection. I have many years ago, we even tried, before having GNU plot even or this kind of stuff, we have tried also with stereoscopic views. So we had 2 surfaces of section. One of the parameters was the angle between the eyes. You were trying to see a torus or something in the background, you succeeded. Now the software saved our eyes. We can have the 3-dimensional projection though. What can you do with the 4th dimension? And we thought color. Its cross-section, each point that goes through the cross-section will take a color according to some color bar that we have here, and then we are looking at how smooth is the transition along the object. So if it goes from blue to red, or the colors are mixed. And then we have taken this three-dimensional projection and we colored them. And then like this we established some rules. So we found out that whenever we had in the center a stable periodic orbit, around it we could find invariant tori colored like this. So if you go from in one or the other direction, the transition, as you can see, is smooth. What you see here is a little bit difficult to be described because one of the surfaces go inside the other. But okay, trust me, now this is exactly what we have as a case, as the fingerprint of the stability around a stable periodic orbit in a four-dimensional surface of section. And also, with the same, in the same way, we found the corresponding structures that were around, close around, in the neighborhood of the unstable orbits, and especially close to this peculiar case that we were characterizing as complex unstable. We have taken all the tools and we have tried to apply in barred galaxies to try to explain the structures of the peanut, for instance. Here is a nice peanut-shaped galaxy. You can see that, well, the peanut is, okay, it is too much light maybe here, but here you can see this is the structure. And also, here are some wings. It is the so-called the X structure. So this is a figure that we see in the sky, in the galaxies, and that to convince also people that are working mainly in n-body simulations, this is an easily produced structure in n-body simulations. So here it is a gadget simulation, in this case just for stars. You have a bar, here's face-on view of this bar, and if you look from this side, then you see that you have this peanut-shaped structure here. It's not the first. The first, I remember, was when in the early 90s by Françoise Combs and the other guys, I don't remember, sorry for Fenger was in the paper, yeah, etc. Yeah, okay. So it is something that comes very easily, and if you want to look a little bit more in depth, this is a similar simulation. Now this time is the best software that the n-body people have in the market, this Gadget 3 stuff in Garching. And here is not the white are the stars, the stars now, the massive the particles, not the test particles, they have mass now. It is an n-body simulation from the beginning. And with red is stars that have been born after the beginning of the simulation. And that you see that in this younger population, the peanut is also there. Okay, the peanut is also there. Okay, so since we have this figure and we can find families that are not only on the plane but also vertical extending outside the plane, we try to see if some one of them could give the appropriate material for building the peanut. And this was proven to be the vertical inner Lindblad resonance, so the vertical 2-to-1 resonance. In this region, we have start existing. This is the best, the correct way to express it. Start existing particles that, by completing one simulation around the center of the galaxy, they have performed 2 vertical oscillations. Such stars start existing at this resonance, at a specific distance or energy, if you want, from the center of the galaxy. And since we are again in 4 dimensions, now things like the characteristics that we use in 2 dimensions, etc., are very complicated. We cannot visualize easily the phase space. Just imagine lines like that. You cannot avoid things that look complicated, but tools that have been developed looks like that. Yeah, it looks, I know, very complicated, but practically here it is like after you go through the theory, you have something that is much more like a computer game than science, and sometimes you even enjoy that. I tell you. There are two indices. The two curves that you see are describe two indices that are related with the planar family, the ellipses, the X1 family. And they tell you, each one of them, what's going to happen if you perturb at a certain energy. Here is energy, and here are the two indices, one for the first and two for the other curve. What's going to happen if you perturb this particle at this energy vertically? Going to stay in the neighborhood or going to escape away? And the rules of the game say that if you cross this, so the radial one is B1. We will not discuss it right now. We put our attention to the B2 index. Each time, and I think I have it also in larger, so that we stay in this region, which is the region with the energies that lead to the vertical inner Lindblad resonance. And here we are. So the rules say that if this index crosses down here the -2 axis, then it will bring in the system a new family of periodic orbits. We have the planar orbits, and then at this energy, a new family is born, and then it plays also its role in the future, not in the time, when I say future is time, no, for larger energies, approaching co-rotation. From this point, from this energy, from this radius if you want, and to higher energies, going closer to co-rotation, three-dimensional families will be also to be found in the system. Okay? And here are those two families that we have found. Also, this one has two indices. The other one, which is born, is down here. Again, these rules go, okay, even to Poincaré, but Birkhoff and other people have done more work on that. And the software actually that has been used goes to 1969 to Brook, who was a great dynamicist, did also a lot of software for the Apollo mission, etc. That's why B1 and B2 come from his name, from Brook, the indices. The rules say that the bifurcated family inherits the stability of the mother family. So until here, the X1, the ellipses are stable. In this period, in this stripe, it is unstable. But here, that crosses, this X1, V1 is a stable family, because here X1, the mother family, was stable. And here this is unstable because the mother family, X1 again, was unstable inside here. Okay? So I show you an example to understand what is the bifurcation. Here it is X1 orbits. Okay? Allow me to put it like this, so that we have parallel the major axis of the bar, and exactly on the bifurcating point, the two orbits are identical. So the magenta and the white one are identical, but only in the projection. Then we start, okay, now it is not anymore the scale the same, but just to make it our life easier. And then I start rotating this plane. Okay? So you see? And here we go. So this is the way this X1 V1 family looks when you look at it edge on. Okay, this is the relation between the mother family and the bifurcated family. Okay, and since our model is symmetric, we can have also the symmetric to the equatorial plane. What can we do with this kind of orbits? Okay. More or less, this is what we can do. We put many of them, and when you put many of them, wings are formed in these directions at the apocentra of these orbits. So you have many orbits, one in the other, periodic orbits now, okay? And along the wings, you find these antennas, let's say. that look very much close to what the galaxy does. Now, this was something that we have realized back to 2002 with papers with Haris Kokos, Athanassoula, etc. It's a series of papers. Now, more recently, we found out the contribution to such structures could be not only to stable periodic orbits, but this complex unstable stuff could, for long times, reinforce such a structure. And this is particularly for this purpose chosen set of initial conditions that we have in the central diagram. Most of the orbits, the red ones, are complex and stable. You can see how they look like. We have the numbers, and there is the image. So you see that even in that, which is the worst case, let's say, you see that for sometimes there is an enhancement of this structure. They are called the smile and frown structure for obvious reasons, because we have those and the symmetric. And the profiles that we could build were like those. But again, it was quite satisfactory. So you could have for a long time the peanut being supported by orbits at the 2-to-1 resonance family. It is not accepted from all people in the community, but this is one case that if you do like this, you produce a structure, the morphology of which is similar to what you see in the sky. Another point was that we have investigated also was that these peanut X structures come in two species, let's say. Biro and I think Freeman was in the paper, or I don't remember, Biro in any case et al. Have called them, yeah, I think so, CX and OX, depending if they cross the center or if they are like four antennae that emerge out of the disk of the galaxy. And the question is, okay, we do have the two families of periodic orbits. The black one that you have up there are the two frown and smiles I have told you. The other one, the unstable one, is like an infinity symbol, the red one. Can we use some of that stuff? This was the other question we tried to answer, to try to make this other kind of X boxy peanuts that cross the center. Actually, one can do things with that, and this can be seen in projections of phase space in the ZPZ diagram. Now, the planar orbit, the X1, is in the center, in the 0, 0 point, because we are in the center. But we have seen that we can increase one of the, let's say, vertical coordinates, here the velocities, the generalized angular momenta, and going the way up here, we meet this red infinity symbol somewhere here. Here and there are the stable smile and frowns. This is not exactly now a Poincaré section of, as in 2 dimensions, it's a projection. We take care of times used, etc., so that we have a clear cut figure. We have seen that also in this case that the unstable periodic orbits could provide tools to build. And these were the manifolds. So there are some manifolds now that are as some very complicated lines appear in the on the cross section that start somewhere here and then they wind themselves around the tori of the stable one families. And all this stuff, the red stuff, the pink stuff, whatever it is that goes around here, it is like in 2 dimensions staying close to the end of some islands of stability. They stay there, and as long as they stay there, they provide tools that can you use. If it stays there for 2, 3, 4, in some cases more, depending how far away you go from the initial condition of the periodic orbit, then it is something that can build a galaxy. You won't, you don't need something to be there for 100 Hubble times, right? Okay, and so look what can happen in this case. What you see down here, actually, you see the structure, it is quasi-periodic orbits of x1 of the planar family perturbed away from the equatorial plane. The x1 is a planar family. It is always there. You can perturb it, however, if you have a three-dimensional system in the vertical direction. Which will be the morphology of the quasi-periodic orbit of x1 in space? It will be like that. And as you approach this cross, which is the initial condition of the red infinity symbol unstable periodic orbits, the more and more they look like it. So when you reach it, when you go by increasing Pz this point here, then remember, chaos is not randomness. You have the paths, the manifolds, as I told. Here is one of these cases. It goes around these lobes, which are the lobes, the empty spaces in the surface of section I was showing you before. So you take that, and okay, it's there, and then you have orbits like this one. So you see that it is something, and now this is very close to zero, so you can also in this case support a peanut and actually a one that crosses the center of the system. Could this be the origin of the two species of peanuts that we find? Open question. But again, here a solution is proposed. Okay. So, okay, just closing this chapter, let me tell you also something that it is, apart from these orbits, are also here, over there, are also some islands of stability that control in the same way their environment around this area. And these orbits also are coming in the game. Were not easily found in dynamical system. You have to change one of the trivial things, but it was just you have to change to find them easier, the surface of section. But in any case, these islands are there. They bring in the system stuff like that, and there are groups that believe that the whole peanut could be just of them, like in Garching, people like Gerhardt and Matthew Portet, and other people that believe in more in orbits like that. These orbits can be put in the same diagram, like to find the relation of with x1, and the relation with x1 is that it is a family that has two islands of stability, let me say that, in the phase space. They do not close after one revolution, they close after two revolutions. We didn't pay much attention, one more reason that we didn't pay much attention until now to this family was that the theory tells us that the most important periodic orbits tools in a system are the simple periodic ones, those that close after one revolution. So those, the others will be something in the neighborhood. But here, this is material that also at least poses questions. That's why we call them x1 mul2 multiplicity 2 orbits. And okay, here they are some non-periodic ones close to them. They have also their complex unstable part, etc. And here are the invariant tori colored so that they have in the this succession of colors in the to make it sure that we are on a surface in the fourth dimension, so the corresponding thing. How am I about time? Can I? Okay, I continue. Okay, so then the next step. So since I told you several things about this complex instability, I want to show you some diagrams that show why some of them can be tools for building structures in bars. So remember, if we have this table one, we stay all the time close to the neighborhood, the invariant curves and this stuff in the 4 dimensions. Now, if we go to unstable situations sooner or later, but this plays a huge role, but let's say eventually they will occupy all the phase space, the available phase space, and bring in the system the new bifurcating families, like the x1, v1 used to build the peanut. In the close neighborhood, however, of this complex stability, if you go away it will be not like what you will see right now, but close to it, things go like that. So here is one case that goes back to 94. So you see, in chaos research, computers play a big game. So if Poincaré had the tools we have today, we would have found everything what we discuss right now, no objects. Now, back in 94, they couldn't color the consequence, they couldn't they could draw that diagram though, this Kontopoulos, Farandos, Papadaki, and Polymilis. And what they realized was that in that case, remember the manifold I was trying to construct, etc., these things were very simple, and simple is nice. So here is the Poincaré section. They went in the neighborhood, they have taken some initial condition, and the intersection of the cross section, of the surface of section, were not random, not even complicated like it was in the case of the manifold, the red thing that I have drawn there. They were on spirals. You see, it goes away like a spiral. So here is a kind of, behind it is a kind of order, huh? Okay, we are now in the complex unstable environment, we are in the chaotic sea. In the 80s, we were saying that now we have discovered another way to go abruptly to chaos. So, because there were no bifurcations. Those of you that have studied a bit nonlinear dynamical systems, you may recall this double bifurcating diagram that you have the first bifurcation, then the tree with the other one, and so on, by the Feigenbaum ratio and all that stuff. Each time the bifurcating families are coming in the system. So you have chaos, but you have also some order. So you go slowly to chaos. Now that you do not have any bifurcations, the first thought was that we go in immediately to chaos. Then it was this kind of figure that remained there since 94, and when Marthos Katsanikas, my student who did his PhD thesis, revisited the issue, found like that. In the center there were already 14, and he continues integrating the nearby orbit. And here is what happens. Each time we register the, okay. Mind also the colors. Okay, and it goes like this. Then if we jump in later times, we're going to have something that will look like that. And at the end, we have such an object. Okay, so the, let's say, order that this figure reflects can make you understand why, by using orbits in this neighborhood, can be tools. They are called confined tori. I think this was, maybe I'm wrong, but I feel that Daniel Pfenniger has given this name, confined tori, to these structures. And he called them tori because if you go a little bit away, then it becomes like a torus. Here there is a hole. All that stuff was very close to the periodic orbit. You go a little bit away, then you have a torus, and these objects are confined tori. Okay, so we use them. We have the stuff to make the peanut. We propose them as the solution. And then another question we tried to answer was this one that Peter Erwin and Victor de Battista posed, was that in many cases, in the central area, we had two kinds of boxiness. The outer one, like in this case, but in some galaxies, like this one is from their paper, you have inner boxiness inside here. How can you, they were asking, how can one have boxy structures in the middle of the galaxy in here? Usually there you have the elliptical orbits. You remember some slides in the 2 dimensions, but these are 3-dimensional objects. And what we did with, again, in 2 papers with Manthos Katsanikas, we first went on the surface of on the plane. We found all kinds of periodic orbits that exist there, and we try to see their shapes. And then we have seen we are at the VLR now. I have here in yellow, because whatever I'm going to say now, it is for the area of the vertical inner Lindblad resonance. I'll show you what happens elsewhere in a while. But here we are in the vertical inner Lindblad resonance area. Here is X1. Here is the landscape in the phase space. And what we have seen first, what we realized, that if we go here where the green stuff is at the borders of the stability islands and just away of it, we could find orbits like that up in the corner. So this was an indication that on the stability islands, just after them, where we have weakly chaotic orbits because they stay for long times around the stability island, the morphology was boxy. We try to see what happens with that. Okay, another one over there. With the non-periodic ones, we have seen that in the phase space, for a long time, these orbits were confined in specific areas. So they could be there for several giga-years. And what could they do is that they could produce structures like that. The left, it is the face-on view. You see it is boxy. In the middle, it is something that reminds the peanut. And where can we find these orbits in the ZPZ diagrams I was using before to find the manifolds? These are the corresponding consequence. You may recall that here is the X1 area, here is the X1 V, the smile, and here is the frown, or the opposite. And here is the position somewhere where the infinity morphology is located. Let's have another look. Things could be like that. Face on, edge on, and here is where these consequences are in phase space. We propose that this could be an explanation of that. We put several orbits on the Ferrer's bar model. The black heavy one is the longest X1 orbit we could find, so that we give the scale. And you see how here it is just a filter on that, and here the green stuff, it is a boxy structure in the middle of this bar, which we proposed as being the origin of this one. And here are some combinations for seeing how long it can be, etc. Now, however, yes, seen that. So here is the correspondence with the face-on profiles. We see that at least we are in the same proportion of the bar, like in some cases, like what Erwin and De Battista have in their paper. This was always a question that I think most of people now believe that it is like this, and we do, that peanuts are part of the bar, not the bar itself. So you have the bar, and those goes back to works with Athanasoula and Misiliotis, and have claimed first that this was part of the bar from their n-body simulations. But since I have shown you also some images from our telescope, here is one that I find particularly intuitive for understanding that. Here is the galaxy. I don't know if it can be seen well, but it has the perfect inclination so that you can see here is the bar, here is the peanut, and then you can see also the spirals. So you see that if this is the bar, this is the peanut, then you can see that exactly the peanut reaches a distance half the way from the center of the bar to the end of the bar. So this is a direct view of that. Okay, this galaxy has also a central spiral in the center. It's another thing, but the arrows point exactly to what I'm saying. The black indicates the end of the bar. The red, here you can see that better. The red delineate the end of the bar. However, there was still a question. Is this a property just of the 2-to-1 resonance region, or can we apply this recipe all along the spiral, the bar, from the center to the end of the bar? But this was really very difficult to do, because imagine in each case to go to an energy and do all this analysis. Then you know that this energy is okay. Let's do the same one. It would have taken too much time. And here is where Leonardo's work is coming into the game. Look what we have done here, what Leonardo has done here actually, is we went to this kind of, we've picked up from the literature an n-body simulation. It has been proven that, well, this was not chosen by purpose, but it is, has a peculiarity. The bar is decelerated in this simulation, so corotation is far away from the end of the bar. So this is in the regime the so-called slow rotating bars. This ratio in fast rotating bars is less than 1.4. And in successive snapshots, it was slower and slower. But this is the snapshots we have got to analyze frozen potentials in these simulations. And here is the characteristic of the X1 family on the plane. And we got help from stability indices. There are, you may have heard about the Lyapunov exponents and other kind of chaos indicators. Here we collaborated with people who have invented and used this so-called Gallia. I will not go into details. I just tell you that the bluer a point in this diagram is, the more chaotic is the orbit. So here is the X1 family. You see that around it, it is quite white. Here is integrated for 1 gigayear, and here is the same stuff continued to integrating for 10 gigayears. So the white stuff is, you can, if you are at an energy, you can think that you are on an island of stability, and if you cross, you go in the chaotic sea. And then by doing this one, we have a landscape for all energies, not only for the 2-to-1 resonance. And we have seen by going along that thinking of what we have found in this single case of in the paper with Katsanikas, we would like to see how the orbits are at the transition region between order and chaos, close to the end of the stability islands and just a step in the chaotic sea, just there. And this is the border, let's say, is exactly where the blue is coming in the game. Here is white, there is blue. We have taken all along this line orbits. And then we have seen that really these are boxy orbits in the plane right now. These are the orbits. These are the orbits. So here is our index. If it goes down to very small values, then it shows that it is chaotic. However, here where the line is for 1 gigayear, and then it can be until 10 gigayears supporting this kind of structure, boxy structures. So this shows us that it has not to do, it is not a property of the vertical Inner Lindblad resonance. It is something that for at least for some class of models exists, like the one we have studied here. It goes for all energies. You go away from the center of the stability island, you take building blocks orbits there, and then you have boxy structures. And what happens if we go in the third dimensions? Okay, we have seen in this case that you can have boxy, double boxy orbits, like that one, like this one if you want. Here is coming in the game the family that supports the peanut, having a boxy with an X also in here, with an X in the face-on view. This is the face-on view and has an X in it. It's not the edge-on. The edge-on view is this one. This is an X in the edge-on view. This and this and this are X shapes in the face-on views. Of course, these were slowly rotating bars. This result we have on the screen right now matches very well with the analysis we did with Katsanikas. So at least in the central area, you can have a boxy feature that is a double boxy structure that projects boxy edge-on and face-on. But since we had the opportunity to look to very slow rotating systems, this was like this from the simulation, we have found out that if you go to really very slow rotating systems, then there is again a structure that reminds us the structure we found in two-dimensional systems being supported in this Tsigaridi paper with the box, the X in it, and a ring around it. This is coming in very slow rotating bars with the corotation being very far away from that. This structure has been found again here, and here is the example I'll give you. So look, here is the Manos Machado simulation, the N-body simulation. Okay, close to the end. Corotation is down here to the television. And this is the bar. They have the side of the bar. And here they have a ring. And their disk dies out somewhere later. Now, we didn't construct a Schwarzschild model, but the only thing that we want to point out is that we have in our artillery, if you want, the orbits to reproduce this figure. So here is the Boxy structure. Look here, there are two minima. Here, if you can see in the white stuff, there are really two minima. There is another kind of stuff that exceeds somehow the bar, this gray stuff. There are such orbits. And then we have this ring. And this ring is coming exactly because a property of very slow rotating systems is that the characteristic is not monotonically growing to corotation. It starts doing back and forths. And then it brings round orbits, circular orbits, because the bar is in the center of the system. And you have a long way to corotation, to cross. And the particles over there do not fill the bar, let's say, so they do circular orbits. This is material to provide to bring in the ring. And look what thoughts are coming in our mind now. Here we have an image of a galaxy. Usually people would say, okay, here is the corotation, and here is one of the so-called inner rings. Here are empty regions, which also are the typical for the Lagrangian points. And here is the Manos Machado simulation. You have a bar, you have empty spaces from the sides, you have a ring, but corotation is over there. And the nice stuff is here, it is too dark to see, but here it is an X supporting structure. And here it is also something that is an X supporting structure. Always in the screen it's difficult to see, but if you look on the computer or in the book, you can easily see. So here we put a question mark. Could in some cases, of course, where you have this ring bar structure be something that has its corotation far away? Question mark. We just, and more or less this is what I wanted to tell you. Let's go briefly through the summary. Boxiness is not always related with the presence of stable Boxy orbits. This can be, of course, the case, but not always. The presence of regular orbits at the outer parts of stability islands and by the sticky chaotic orbits just outside them give you material to build Boxy structures. Double Boxy structures can be supported by this mechanism. And finally, that in very slow rotating bars, the box can be the bar itself, not part of the bar. Okay, Boxy, a brick surrounded by a ring, and corotation far away as a possibility. Thank you for your attention.
Actually, I was wondering about the other regime you mentioned of slow rotators. So when omega, the pattern speed, is high, then rotation moves into this, well, towards the center,
Yes.
and then you have overlaps of other resonances. And have you or anyone studied the effect of a high omega into the stability of the inner structure?
Yes.
And doesn't that help, to set a limit on what omega is or must be for our galaxy? Or
Yeah. a limit that is always put in the pattern speed of the galaxy is that you can bring the Lagrangian points, that means corrotation, at the ends of the bar. Because only until that point, theoretically, you can have bar supporting orbits. You cannot cross inwards this limit. So, because if you cross the limit, outside you have round orbits. The orbits we know outside corrotation are also perpendicular to the bars in a sense. Imagine not that much elongated elliptical orbits perpendicular to the bar. So this stuff does not build the bar is built by elongated stuff. So the fastest it can grow is corrotation to be at the end of the bar. There are some exceptions discussed somewhere for time-dependent models that can bring for some time the transition period, but after the bar will be settled again as a mode and will have a specific pattern speed, the largest they can stay is at the end of the bar. Now, what are the implications for all what we discussed about Boxy structures? We did actually, we have the example of the work that I have shown you with the colors, etc., with me and Katsanikas. This was a fast rotating bar, so I don't remember, it was 1.2 or something like that. But submitting the paper, we got a similar question from the referee, and we did an exercise, and we have seen that in that case, really the double boxiness should be restricted in the central parts for a series of, for many reasons. One is that the families at the vertical resonances away from the 2-to-1 resonance, so the 3-to-1, 4-to-1, etc., do not grow up very much. So they stay very close and practically support two-dimensional structures. So you do not have so much freedom in varying. Another thing is that we have seen that in that case, in the higher order resonance, if you go closer to corrotation, they are boxy, but not that boxy as the examples I have shown you. So we tend to believe that in fast rotating bars, double boxy orbits are in the center, and you have slow rotating bars, then in the extreme case at the end, it can be the bar itself. You can imagine a brick surrounded by a wheel, and that's all. So this is the relation, as we understand right now, between how fast the bar rotates and where can you find the double box structures. Yeah.
Muy bien. ¿Alguna otra pregunta?
There are other structures related to bars, as for example, bar lenses.
Bar lenses, yeah. Look, bar lenses, the work that Heikki Salo and Eija Laurikainen are doing with the bar lenses, maybe you followed this work. Yeah. This is related exactly with the area that we found this double boxiness in the fast rotating bars. So their bar lenses are, okay, these are orbital models. The closest thing to what we can bring to density are our response models, which are not density models in any case, but the closest is that one. And we realize that if we have something that it is related, it is exactly this area. So the bar lens could be the face-on view of the orbits we show there. And this is matching with what we propose as the 2-to-1 resonant orbits being behind the structures, because then you have the bar lenses in the right place. So if the bar lenses are the peanuts face on, as Heikki and Eija say, then we are in agreement. We give tools to build bar lenses. Especially, and also towards this direction points the fact that these orbits we use are either at the end of the stability islands or they are chaotic, weakly but chaotic. That means that you would have expected more or less constant with the time density along this lens feature. So it is in the definition of the lens. I think we are in agreement, as we have discussed it with both of them several times. Most probably we are in agreement. So we propose orbits to build the peanut in the center of the galaxy. In the same area, they put the bar lens, which is the counterpart, the face-on counterpart of the peanut. So, yeah. Gracias, gracias.
We actually had a lot of people, because at the beginning was
Yeah,
they
yes,
extended
yes,
it until
yes, yes,
1 o'clock and then
yes, 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 I know.
But I was surprised because there were nobody
I
here and
thought I thought that okay,
Everybody.
it went a little bit deeper to theory or these things, but I think it would be a nice background for discussion we're gonna have
yes,
afterwards.
that's exactly what I
Yeah,
was
yeah, yeah.
thinking,
So,
because I have
so
like
that
10
since is
questions based on
the
this.
most important thing is that we have the discussion afterwards. So
Exactly.
they will excuse me.
It was great. Actually, it was nice because I think that people here need also
The,
background.
the background, yeah.
They liked it.
Yeah, I hope so.
They